not original or diverse enough. A good solution for this could be the real-time evaluation, which consists in user feedback. Some relevant aspects which have to be taken into consideration while designing a recommendation systems are the following. Diversity, first of all, is a very desirable aspect, especially when the system recommends almost duplicate items. If we don't have diversity in our recommendation system, some duplicate and same movies will be recommended to the users who have already seen them. After all, the preciseness of the whole data set does not matter. It is desirable to minimize the error only in the recommendations that are considered to be as ranked top n, which n can be chosen by the designer of the application. In my application, I choose to find top 10 movies for users. In other words, the system wants to have maximum accuracy in determining the most likely preferences and not the items with the lower chances to be appreciated. Here we can see the limitation of a recommendation system. The convenience of this recommendation system is the very simple implementation and the reduced cost and resources needed. Even though they have some certain limitations, two of them can be seen in the slides, the first rater problem and the cold start problem. In the picture below, we can see the first rater problem described, and it is the equivalent problem in the case of new items entering the system. So if we don't have any ratings on the system, some movies on the system, we cannot generate recommendation basically. The cold start problems occurs only for new users of the system. When, for example, there is no actual information about their preferences in order to generate possible recommendations. An innovative approach for solving this cold start problem could be implementing, like Netflix did, a getting to know step in the beginning when you create an account and you first log in into the application. They put you to choose 3 movies from a wide range of them. So based on those 3, they will recommend something similar for you. As the part of result, I chose the dataset movie length, which has 100,000 ratings, 943 users, 1,682 movies, and 80 possible genres for the movies. The ratings frequency varies from 1 to 583. In the table below, we can see the dataset movie length with the 2 versions of it, with 100,000 movies ratings and the movie length with 1 million. The dataset evaluation. We made the dataset evaluation
I will try to show my screen. Do you see the dataset evaluation?
Yes.
Continue your presentation.
In the first graph, we can observe the numbers of movies along with the numbers of ratings. And in the second graph, the visual distribution of ratings. These evaluations were made with the Python library, and they're on the movie length dataset with 100,000 ratings. In the next slides, we conducted a survey on real users in order to measure user satisfaction against our recommendation system. The methodology is listed below. We picked the target user number 340, because he was the most similar to my tastes. We have the same movies liked. We run both KNN algorithms on the target user. We analyzed the metrics and we analyzed the recommendation movies, and I chose which is the most suitable movies. Here you can see the top 10 movies for both approaches. And in the following slides, we will see the metrics. First of all, there is the RMSA, the root mean square error, where the lower values have the better accuracy, and the user KNN is favored in this case. The mean absolute value, which the lower value means better accuracy, which on the following slide you can see that also the user KNN has better accuracy. After all, the hit rate, which is the same for both algorithms. In the second table, on the first table, we can see the coverage, diversity, and novelty. The coverage means the ratio of users from whose recommendations have above certain threshold. The higher the results, the better. The diversity, which is how many duplicates the recommendation systems recommend and how we filter them. And the novelty, which is the average popularity rank of recommendation items. Higher means more novel. We can see the comparison in the following slide. And in my opinion, the user-based KNN on this data set is better. After all, in the following slide, I will explain how we designed our system. We use the transparency quality, which is the system providing explanation for recommending an item. Here, for each user of the application will be generated two graphs, one with the counted number of movies and genres which he rated with 1, 2, 3, or 4, or 5 stars. And on the second graph, we can see the movie ratings by year. For example, if some person have a preference for old movies or new movies. Recent researches prove that the acceptance and approval of a suggestion increases when the user receives a justified recommendation, so that's why we made those graphs. As future extensions in the next slide, the system will take into consideration the following factors, combining the results of the algorithm, like recommending 5 movies from item-based KNN and recommending 5 movies of user-based KNN. The interest of groups, like adding some hashtags to the application, the director of the movies, some people might like certain directors and only want to watch movies from them, the IMDb review, and the age of users. As a conclusion, the initial development of recommendation systems started from a rather trivial observation. People who had similar tastes in the past will probably have similar tastes in the future. It often occurs that the collaborative filtering method provides a better predictive performance than content-based method, at least when there is not enough available data and information. This consideration is, however, purely intuitive. And as all things to be considered, through the performed studies and implementation of the proposed application, we can evaluate the benefits of a recommendation system in our lives.
Thank you very much for your presentation.
Thank you for listening. And I'm sorry for the technical issues, but I'm not sure what didn't work. If there are further questions. Well, usually these systems do have the bubble effect because, every time, for example, when we talk about something, they recommend us immediately those things. Usually the recommendation systems work like they do not recommend the new purely new things. I mean, if some people search for drama movies, the recommendation system won't recommend them another kind of movies because they are somehow designed to recommend things which user ask either explicit, like by searching to a page or looking at the picture of a movie. I mean, they don't usually recommend strange things, like out of the bubble, how we consider them. I think it's a good idea, but I mean, this research study was only on user. I mean, it was user based on his behavior, but I think it's a nice idea as an improvement for the future. Thank you very much too. If there aren't any further questions, I would like to thank you for watching and listening to my presentation.
Thank you very much.
Thank you.
With problems, but very well. Okay, thank you.
Thank you.
Thank you. Thank you very much. I think that I have to announce the next presentation. I think it's Chiara Julia Denisa, load shedding for aggregation carry over data stream traffic congestion.
Yes, I'm here. Please let me know when you can see.
I think that you
screen.
can share your desktop.
Yes. Can you see the presentation?
And I see that your desktop load shedding aggregation carry.
Yes.
Yeah, I see the first slide.
Okay. My name is Tira Julia. I'm from Babeș-Bolyai University, and I prepared a study on load shedding techniques for aggregation queries over data streams in the context of traffic congestion. Can you see my second slide, the agenda slide? Okay. This presentation is organized as follows. I will start with stating the problem approached in this study and the most important theoretical concepts used. Then I intend to describe the experimental part and present the results obtained. I will point out the technologies used and list several real-life applications that are based on this approach. Briefly summarize the observations and discussions and mention several research directions. I prepared two scenarios that formulate the problem approach and describe the theoretical concepts used. Let's take the first scenario. Anna, she has the task to monitor the urban traffic and analyze the average speed for all vehicles from Julius Mall to Memorandum. This example describes the term of data stream represented by the amount of traffic information she receives because as a general definition, a data stream is continuous data generated by a source. At 1 p.m., she receives a greater amount of data because it's a rush hour. Everybody is leaving the work or going somewhere, and the route is quite busy. So in order for, this is an example of a bursty situation. As a general definition, a bursty situation represents greater amount of data generated in short periods of time. And this situation can determine a system overload and a system crash. She is thinking about a solution and comes up with the next idea. Let's discard some input data. She can make this selection randomly or based on several characteristics. Let's take the second example, the second scenario. Bob, he works as a librarian and has the task to arrange the books in bookstands. At some point, he receives a big delivery. Let's say that 100 books represents a big delivery. But he has only 70 available spaces. His solution is to deposit several books. He can select the books to deposit in a random way using a coin or based on previous data, such as the best author, the most wanted genre, or based on current data, such as reviews. This solution represents the concept of load shedding, meaning discarding some input data in order to prevent a system overload, but the immediate effect is a degradation of the accuracy. For the experimental part, I simulated an overload situation and analyzed the accuracy and the runtime. I gathered information about vehicle type, registration year, transmission, delay, speed, fuel model, horsepower, and brand. And I use the concept of time-based sliding windows. This concept is explained as follows. We have a generator that for 10 seconds generates different amount of data. One window is represented by one amount of data. Let's say the first window that has 5,000 tuples, 5,000 data, and its length is of one time unit, in this case 1 second. As soon as a window is generated, it is sent for processing. Then the next window is generated and is sent for processing, and so on. How do I have a bursty situation? Well, we have a runtime threshold. And in the case of a window being generated and sent for processing, if the runtime of the query is below that threshold, then we have an ideal scenario, no bursty situation. On the other hand, if the runtime exceeds this threshold, we have an overload situation, and as a consequence, we apply 3 load shedding techniques, which I will describe in the next slide. To describe this load shedding concept, let's consider this query as an example. This query returns the number of diesel vehicles. The normal execution of this query is this. We have a window of 100 data that is filtered, and then the remaining data is sent for processing. This is the query plan. We have the data stream, the query operator represented by the filter operator, and the aggregate operator in this case is the count operator. This is the first method of load shedding, random load shedding before query operator. The execution of the query is as follows. We have the window, then the load shedder operator, which discards some data. After this, after some data was dropped, we have the remaining data that is sent for filtering, and then the remaining data is sent for processing. So the load shedder is placed before the query operator, immediately after the data stream arrived. For the second method, I chose the random load shedding approach, where the shedding operator is placed after the query operator. In this case, the execution is this. We have the window, the filter, the data after being filtered, the load shedder operator, the remaining data, and which is sent for further processing. In this case, this is the query plan. We have the data stream, the query operator, and the load shedder placed after the query operator. And the last method analyzed is the semantic load shedding, and I use the approach of window drop. A window drop represents discarding the entire window, not only several tuples from the window. So let's say we have 3 windows, the first one, the second one, and the third one, and the window drop operator. If the window drop operator decides that the window must be dropped, then no data is sent for processing. If the window operator decides that the data does not need to be discarded, then all the data is sent for processing. How does this window drop make its decision? Well, it uses the Bayes theorem, but you can find more information in my thesis. For the results part, because we don't have enough time to present all the experiments, I prepared 8 experiments, but I will focus only on 3 experiments. All of them are described in my thesis. I will use the next 3 queries. The first one uses an average operator and gives the average speed for all vehicles registered after a year. Then the number of a specified type of vehicles. This uses a count operator. And the last one, the maximum power of vehicles registered after a specified year. This uses the maximum operator. I will open another window. Please tell me if you can see several charts. Okay, let's take the first experiment, get average speed for cars. We have, in the case of the first method, load shader before query operator, in the first chart, we see the difference between the real result and the computed result after placing the load shader. The difference between the results, and as a consequence, the accuracy is between the values of 80 and 90. The runtime is quite good because the difference between these times is observable. Let's take this example. We have the real time and the computed time, so we can say that this method is quite efficient. But if we place the load shader after the query operator, the results are not as close as in the first case, and the accuracy is lower than in the first case. We see that the accuracy is around the value of 80. And also, this method is not so efficient in terms of processing time or in terms of runtime. Now, comparing for this experiment all the 3 methods used, we can say and see that the best accuracy was obtained in the case of the first operator. We obtained this accuracy, but the best runtime was obtained for the last load shedding technique. Going to the next experiment, for the first method of load shedding, we see the difference between the real result and the final result. The accuracy is lower than for the first experiment. It's around the value of 50. The runtime is quite good. The difference between the runtimes is quite good. And applying a load shader after the query operator, the accuracy in this case is also around the value of 50. But the runtime is not as good as in the first case. Comparing all the 3 load shedding methods for this experiment, we can say that again the best accuracy was obtained for the first load shedding method, and the best runtime was obtained for the last load shedding method. And now the last experiment, maximum number of power for the first method. This is an ideal experiment because it uses a maximum operator, and despite the fact that we discard some data, we have a quite high probability of having the maximum value in the data, in the remaining data. And this is what happened in this case. The real result and the computed results are the same, and the accuracy, as a matter of fact, is 100%. The real time and the processing time are quite good. We can see the difference between them. And in the next case, if we apply the load shader after the query operator, the results are the same. The accuracy is 100% again, but the runtime is not as good as in the first case. Comparing the accuracy and the runtime for this experiment in terms of all the load shedding methods used, if we see here, the accuracy is 100% in all of the cases. So in this case, we can choose whatever method we want. But if we want to be efficient in terms of runtime, we'll choose the window drop operator. Now I will return to my presentation and go on with the technologies used. Can you see the slide? For backend, I use SAP ABAP, and for frontend, SAP UI 5. Several applications that can use this approach are a parking monitoring app. If this application tells me that you will find a parking place with a probability of 60, probably I will take my car. Otherwise, I will go with the bus. And real-time web search, well, I'm interested in only one or let's say 2 pages. I don't want hundreds of pages with studies and demonstrations. As a conclusion, there are several important aspects for an application. Each application needs to be flexible because in case of an overload situation, it must adapt. The adaptivity I explored and studied in this research is called load shedding. And as you could see, I analyzed 3 methods. And as an overall conclusion, we saw that depending on the aggregate function, the accuracy and the runtime vary. But if we are interested in a result as accurate as possible, then the best solution is to use a load shader placed before the time is the interested aspect. Then we should choose a window. Several research directions. We can train models to predict the discarded tuples. We can place more load shaders in the query plans. We can have more complex plans, not only with where conditions, but with joins. And we can analyze the best location to insert shading operators. Thank you for your time. If there are any questions, I'm glad to ask them.
Thank you very much. As usually, I have to start with the questions, and my question is: in your presentation, you show us, let's say, only simple queries.
Yes.
So your approach works only with simple query, or goes also with more complex queries? So you'll be able to find the number, the count of car, the count of diesel car, but how about the average speed of or the average number of diesel cars? So if you have not a simple operation, but 2 or 3 or many related operation inside your query, also can you somehow
My experiment works also with complex queries, but but if we work with complex queries, the runtime and accuracy will suffer a bit. There will be a degradation of the accuracy, and the difference between the real runtime and the computed runtime after the load shedding will not be as observable as in the cases of simple queries, because I experienced on simple queries and used the load shaders placed, let's say, between after the query operator and immediately after the data stream. But if I have more complex queries, then I need to place more load shaders to obtain a good runtime, an efficient runtime.
Thank you.
Yes. Because if we have let's say 2 load shaders, then the first let's say we have a window of 100 tuples, then the first load shader placed, which after that window is processed by that load shader, let's say we have 80 tuples remained, and then we have another load shedding operator which process that data depending on the remaining data. So the final result will be more accurate than in the case of placing only one load shader operator. In this case, I think that because let's say we have two load shaders. The first one processes the entire data, the whole data, and the second one processes only a part of the data. But this is an interesting idea, and I can add it to my research directions and compare the results obtained.
Also, I think that what he says it's very correct, very good. Having a multiple loader, it's a good thing, but the problem is where do you put such items? So if you have a sequence with 3 or 4 operation, maybe if you put such loader after or before each sequence, it's problematic. You have an extended runtime. But if you put only 2 or 3, and the problem is to find for specific query where do you have to put the where is the best place to put your loader in solving the query.
Yes. Yes, you're right. I need further information to get the best location.
Yes.
Yes, indeed. Thank you for the idea.
Thank you very much.
Thank you.
We have to thank Julia for their presentation. If there are no other questions, I invite the next presenters, which is Mocanu Diana Georgiana, will present machine learning based query exploration. So it seems that it's in a way a trend. There is a common keyword carry in the title. Please proceed.
Hello, can I share my screen?
Yes.
Okay, please tell me when you see it.
I see in the future machine learning based query exploration.
Yes. Okay, so hi, my name is Diana Mocanu, and today I'm going to talk about machine learning based query exploration. First, I would like to start with a question. Did humans reach their limit of being able to process information? Well, to some extent, this may be true, as with the continuous advances in technologies, we reach an exponential rate of acquiring new information. And this implies that for querying scientific data, big data, it became an impediment. Why? Well, the answer is in how the data is stored. We have abstract abbreviations for the attributes, and sometimes the relations stored, in most cases, are quite complex. And not to forget the data that is stored in these data sets. It comes from different measurements, and this data is quite difficult for a human being to understand when it's in such a huge data set. Because of all this, creating a query with a perfect condition to find your desired results has become a really time-consuming job, because a user has to understand the data to further find the little patterns that could induce in the wanted result. And in most of the cases, it's possible they do not really have a clear idea about what they are really searching for. Maybe they know, a vague idea. For example, if we have a scientist that is looking for stars that have planets, maybe for some of them it's clear, yes, they don't have planets. But for some of them, there is still a mystery. It is unknown. And the answer could be found in the already existing measurements
and data. But I think that this is not a problem, as in most of the cases in history, some of the biggest breakthroughs were made by chance. For example, the X-rays. Therefore, I think that the motivation behind this paper is quite clear. The data is difficult to comprehend. The process of writing a query has changed for big data. It's no more a query and a result, a fixed result. Now it's more of an incremental process, a try and error process, where we try a query, execute it, make some changes, execute it again until we find the wanted result. And all this means a lot of time. Okay. The objectives for this paper were to simplify the process of data exploration using different queries to reduce the time and to help them find the pattern. The architecture that was used in this for this prototype that we implemented further was a client-server architecture based on model view controller design pattern, where the model and the controller are on the server side and the view on the client part. For this, we written the server in Python, the client in React, and use MySQL for storing the data. We offer the user some functionalities that will help him understand, one of which is to write and execute a query to explore a database. For a specific database, he can see all the tables that are contained. For a specific table, he can see all the columns. And for a specific column, he can see the interval that those values are in for that row. But our main functionality is to generate a new query based on an initial one given by the user. And as an extension, we offer the user the possibility to select different conditions that were obtained in the process. The steps that need to be followed are quite simple. First, we need to construct the learning dataset, based on which we'll generate a decision tree. And based on this decision tree, we'll create the new query. For the dataset construction, first we'll need to define some labels, a positive and a negative label. The positive one will represent all the tuples that were obtained from the execution of the initial query. And the negative ones were the ones that are a counterexample, clearly not wanted by the user to be part of the final answer. So if we have the following query, which is kind of a simple one, written based on the famous IRIS dataset, with a composed condition, with a disjunction and a conjunction, this is a snapshot of the resulted dataset, where the first three were labeled as positive because they were obtained from the execution of this query, and the last two as negative, as they would be further obtained from the execution of a negated query. But what is a negated query? Well, it's a query that has an opposed meaning compared with the original written query by the user, and it's obtained by negating the original condition. For this, we offer two different negation solutions, a random approach and a greedy approach. We'll start with the greedy approach. Here, we'll only negate parts of the condition. So if you have the query that was written in the previous slides, we can negate the first condition or keep it as it is. And the same can be said about all of them. For deciding which negated query to keep, the decision will be based on the overall result size, and it should be as close to the original one as it possible. The algorithm for negating parts of the condition is based on binary numbers. That will be from 1 to 12 to the power of n minus 1, where n is the number of subconditions of predicates. And based on this number, we'll choose which condition to select. For example, for 100, we negate only the first condition and the others as it is. So 1 negate, 0 keep as it is. Quite simple. Well, this one was based on the law of large numbers, meaning that with the increase in the size of a data set, it also increases the probability that a random selected population to be uniformly distributed around the dataset and therefore to better represent the entire population. Here we negate the entire condition and we'll order them randomly and select a number n of negated tuples. This number is calculated based on this formula, where E we define as the percentual relative coefficient, can be 1 from 100, and is given as input by the user. T is the total dataset size, and P the positive dataset size. the obtained in the previous steps. Okay, so now we reach the decision tree generator. We use the CART algorithm, which is a supervised model construction algorithm because it has already labeled data and the set that was constructed in the previous step. And based on this one, we'll generate the tree. So if we have this example, the tree will look something like this. Well, the table is just a snapshot, but this is on the whole obtained data set. And as it can be easily seen, at each level, a condition is applied. And based on this condition, it will be further split. Or if already the labels to reach are clearly a positive or a negative one, it will stop. The condition creation. After we obtain the tree, we'll parse it, and we'll explore different paths. A path is from the root to the leaf, and practically a path represents a condition, an alternative condition that is formed from the conjunctions of all the conditions that were applied at each node. And we'll keep only the conditions that will reach a positive leaf. So if we have the previous example, a possible alternative query will be this one, where the condition is these junctions of two paths. Results are quite promising. We had two main experiments done on 3 different databases with sizes from 115 to 33,176. And we used the same 3 queries for all the experiments for better accurate results. And all the queries are based on the same rule to have a conjunction and a disjunction and 3 subconditions. For the greedy negation results, we observed that we have better results on smaller databases. Because of the greedier approach, on big ones, the time is quite big, around 2 seconds, and 2 seconds is a lot of time when you wait for something. And the results are quite contradictory from one query to another. We can obtain no new tuples, or we can obtain a lot of new tuples compared to the original size of the query. The random algorithm results were quite promising and good. We observed that the negatives data set will influence over time, which was quite expected. For almost 30,000, it's 2 seconds. The smaller the database, the bigger is the variation for the same parameters from one iteration to another, because the smaller the data set, the is not so randomly and better characterize the population. And as we expected, there is an inverse proportional variation between E and the number of new tuples obtained. The smaller the E, the greater the number of new tuples, and the smaller the chance of 0 new tuples increases, offering the user a rewritten query that will offer him the same results. As it is such a huge deal of working with data nowadays, and everyone is searching for new alternative ways of working with big data, there is a lot of research done in this domain. The more important one is the first one. Our paper is based on this one. We extended it. And in this paper, the negation algorithm used is more of a knapsack approach, and also the decision tree algorithms are different. The following 2 are based kind of the same idea of a user that needs to be guided along its interaction with a database, the need of a guide like a touring guide, and to receive hints along the way. And the last one, the why not questions, practically represent the possibility to ask why and why not, why we have these tuples, why we don't have these tuples that we expected, and that will, based on a data set, will create a query that will obtain that one. As all applications, there is always more room for improvement. In the future, we want to implement and play with more diverse negation algorithms to observe how this influences the time and the overall result obtained. to use different algorithms for finding a pattern in the data, and also to offer the user the possibility of a history-based query retrieval. This meaning that he will be able to explore parallel paths starting from a query that was written in the past. In conclusion, I think that we offer the user a more interactive and explore way of exploring database, and with our smaller functionalities, it is more easy for him to understand the data. And we also offer him the possibility to assess the quality of the query obtained by looking at this pie chart that will tell him how many of the old tuples are still there, how many are missing, and how many new tuples he obtained through this query. Now I would like to make a small demo of our prototype. That is a demo. Sorry, I hate this thing. Okay, so here he can choose between different negations, and based on the negation, he will also can choose the rate of new tuples. He can choose from different databases. He can generate the chart and choose the tables that are from that specific database. Sadly, now we have only that one table for each data set, but I think that we can improve it in the future. So for example, for this one, we can see all the intervals that I have mentioned about the value. That will be really helpful. And to take a query, because I have already written a bunch, we can put it here. We can modify it. We can click generate. But as we say, we didn't choose the correct database because it's the pulsar. Okay, so this is how a generated query will look. Here we have the result. We can play with it and try different and see for this one is not. We can change this and also run it again. And we can even put a huge amount and see that this is it. And we can also execute a query and see its result. We can open it to see the table, and we can see the data distribution for that result. And this will further help a user if he wants to change some values to see if, oh, I still have possibility, but he also can execute this one. And I want to thank you for your attention. If you have any questions.
Thank you very much for your presentation. I have questions. I prepare my questions and I start presenting as a future development when you try to explore more diverse negations, to also explore calendar data, because for I saw only until the last slide, I saw only examples with numbers, and with numbers it's quite clear that some values should be only less than or greater than. But for calendar data, there are different kind of negation, not just less than or.
Yeah.
There could be the same week, the same mount, different mount, or something like that. So should I understand that you also approach something like calendar data?
Yes, I also had some small experiments working with calendar data, working with years. But yeah, the algorithm
basically maybe you split the calendar data in year, month, day, and you somehow make negation based on these three values, or
well,
yes? No.
Practically we negate the result. I mean, if a year is 2016, the algorithm can find that if the year is greater than 2017, we will obtain better results for what you want. So yeah, it also works with years, with months, its values. As long as they are number values, it works.
Okay, thank you. Other questions?
Sadly, the CART algorithm doesn't accept labels, something that it isn't a number. I also have an ID, but I removed it from the generation of a decision tree because sometimes it also based it on the ID. This is what I observed in time. And if it has a label, for example, I have the iris that also has the class. Sometimes it will base it on the class. It will observe that all the tuples from the class sepal, iris type, it will base them on that. So I saw that my algorithm also sometimes base it on classes, but as long as they are integer values or numbers.
Can I put another questions? Maybe somehow related with your questions. You ask about discrete value. So I will enter in sensible domain. Let's say discrete value could have only two values, yes or no, male or female. But you don't know that there are just two. The gender has just two values. Maybe you don't have these metadata in your knowledge base. So how can you deal not with continuous value like numbers, but with pure discrete values like let's say gender? So male, female, or you can have both male and female negated, or you don't know the numbers of possible value in such a discrete domain.
It's a really interesting question. Well, this algorithm practically having a data set will create a tree. So if that tree will contain information about male and female, he maybe will try to split at each level based on this category, and he will observe further that if male, then I can put this further condition and reach this wanted result. So I don't think that it will be a problem if they are just male and female and we don't know more about it, as long as the algorithm in the back, the CART algorithm will split the tree.
If in the data set there are only two such discrete value, he will generate also he will generate always trees with two subtree based on these two possible values.
If all the data set has only two attributes?
Yes.
Yeah.
Male and female.
Yes. Yeah, then yes, only these two.
And if if the data set is somehow enhanced with, let's say, a third gender, he will start generating trees with
Free. Based on this free, but the trees are binary trees.
Binary.
Something like this. So the trees are binary, but yeah, it will be only the free attributes. So he will be just 0, 1, and 3 possible attributes that he will split them on.
Thank you. Maybe he will be, my colleague will be able to.
As far as I looked for this decision tree part, no, the trees are only binary. But I don't think that it will be a problem if I found, or if there is another algorithm that will create a decision tree and it's not binary, because the algorithm will work on every tree that he gets as it parses. Yeah, it takes a lot of time. Yes, and this is what I said, that in the future I want to experiment with other pattern finding algorithms that maybe will be able to generate, to give me the possibility to generate these conditions without creating a tree, parsing a tree, that maybe will be a little bit quicker. Thank you a lot for your attention and questions.
Thank you very much. A very nice presentation, both PowerPoint and also some execution of the problem showed in your presentation. And thank you very much again. And I will like to get through the next presentation. It's presented by Paul Gheorghe Motora, a solution for detecting fraudulent transaction using neural networks. Please share your screen and show us.
Okay, I'm sharing desktop right now. I guess you can already see the presentation. Okay.
We see a solution for detecting.
Yay. Okay, so let's begin. My name is Paul Motora and I'm a student at Technical University of Cluj-Napoca. Today I would like to speak about fraudulent transaction and, to be more specific, how deep learning can be used in detecting and ultimately stopping them. Millions of dollars are lost each year due to fraudulent transactions. Fraudulent transactions are occurring when stolen credit cards or even stolen data are used in generating unauthorized transactions. This paper proposes a solution for detecting the fraudulent transactions using a neural network and other outside, let's say, knowledge. We are going to discuss about related work, innovation, and architecture, and after that we are going to see some experiments, results, and make some conclusions. As a related work, we have studied a lot of papers, but the three most important are these ones. The first one really gives us a general idea of what different architectures are or how different architectures are used in detecting fraudulent transactions. The second one compresses 10 years of knowledge, of innovation and research in just one paper, having a lot of other papers being cited in it. The third one is really interesting because it gives us an overlook of how an actual architecture of a payment system might look like. So it's a good starting point for developing a complete application. Okay, right now I would like to speak about innovation and mostly about the 6i check system. 6i check system, it's a really simple idea used in payment originating systems all over the world. It assumes that 3 different persons have to see the data before a transaction can be settled. This is used in our system by the fact that 3 different predictions are being combined to generate the final result. The implementation of the outside knowledge combined with the let's say not state of the art, but maybe latest and greatest innovation in artificial intelligence are making the system innovative and not, let's say, a new discovery in a single area. Architecture and implementation is really simple. We are going to rely on a 7 hidden layer deep neural network architecture, 1 input layer, 1 output layer. The output layer contains only 1 perceptron with a simple answer. It is or it is not a fraud. 0, it is not a fraud. 1, it is a fraud. Future engineering is used in our system to generate more futures needed for the system to learn quicker and to be more accurate. From 15 initial futures contained in the data, we are going to extract and to get to 75 of them. A really important aspect is that the shape of the whole architecture, it's like a funnel. Many low-level features can be compressed into far fewer top-level ones in the upper layers. So the system it's really quick in both training and testing. An important aspect to be mentioned is that dropout technique was used in developing the whole system. The dropout technique uses the classic boxing or maybe kickboxing training idea that training hard and fighting easy. So during training, we are going to ignore some of the perceptrons, and during the testing, we are going to use all of them. By doing so, the system is less sensible to changes and can be more consistent over time. That's a really schematic way of how 6i Check is giving flexibility to our system and how the 6i Check is helping the system to be adaptable to a certain customer's requirements. We have 3 different predictions that are going to generate 3 different modes or 3 different functions for the system. We have the increased precision, increased recall, and the balance mode. The increased precision means we don't have a great amount of false alarms. The increased recall means that we are going to have more false alarms, but all the fraudulent transactions will be labeled correctly. Okay, and for dealing after all the implementation, the system was already giving some satisfying results, but I thought that we can go even further and generate some synthetic data for the system to use easier. ADA scene was used in enhancing the training set alongside with future engineering. ADA scene was used because it focuses more on the outliners, so it generates more of the isolated payments that the system doesn't have in the initial set. Okay, experimental setup and testing. For the experimental setup, we are going to split the initial data in 80% training set and 20% testing set. From the already split data from the training set, we are going to take another 20% and use it as validation in a k-fold process that helped us tune hyperparameters during testing and training and during different trials. Important to say is that from 15 basic columns, we are going to get 75. So the system will have a lot of data to learn by. Another important aspect in banking systems is the speed. Given the fact that millions or maybe thousands, depending on the system we are going to implement the architecture alongside, we will have maybe 3 minutes or 2 minutes to get a response. The architecture is really fast in training. We are going to get the system to be trained on 75,000 payments in under 8 minutes, and after the usage of synthetic generator, having the almost double that number, we are going to need only 13 minutes. Also important to say it's that the system has the capability of processing a payment, an unprocessed payment, from in 2.1 seconds. The most important part and time-consuming part of this will be the preparing the prepayments needed for the data to go through the AI module. Right now, I want to speak about the usage of the 6i Check and its advantages, or the absence of the 6i Check. We can see right here that a classic early stopping has really good results in some cases, but also depending on the training test, we can have disastrous results. 6i Check remove these problems and give the system consistency and stability alongside flexibility. Also, we can see a little bit of improvement in recall. For the results, I tried to be as realistic as possible. We have no augmentation cases in which we already have the satisfying results. After that, I tried to augment only the training set, so the testing set won't be touched by any process until the testing itself. And in the end, we tried to augment both training and testing set. The last augmentation of the whole data is done because in a classic, or let's say in a functional, in a live payment system, we can have access to millions of payments. So we can have training data or a total. We must not generate extra data, but we can choose whatever data we want to use in the training. Really important to to say is that the fact the accuracy is not relevant anymore. 99.78% of the initial data are just legal payments, and only 0.22% being fraudulent transactions. This gives us the accuracy itself, the classic accuracy, can give us a false impression of really good performance. That's where the F1 measure alongside precision and recall steps in. Okay, and here we have the results. The future engineering, as we said, going from 15 to 75 futures give us an extra boost of accuracy or performance, let's say, of 25%. The usage of 6i check proved to deliver another 20% droppage in the error rate from the already improved algorithm. In the testing, the neural network was able to detect between 94 and 99% of the fraudulent transaction. The variance is given by the fact that the final customer will be able to adapt the algorithm with the press of a single click due to the 6i check system. Already having good results, but having another method of improving them really proved to be satisfying for us, and we applied AdaSyn only for the training set, just to be sure we are not providing false results. So the performance is increased again by 1-2%, maybe like a 2% constant from the minimum, but the maximum was not that far better, was still 99%. As the result, we are going to see that great recall always has the drawback that has a poor precision value. The recall is often traded for precision, so when having excellent results in stopping all the fraudulent transactions, we will also have a great number of false alarms. Okay, as a conclusion, we can see that our paper presented a valid or maybe a solid proof that deep neural network is a possible solution to detecting and to successfully labeling and stopping fraudulent transaction in a really short period of time. Not the best thing about our system is how exterior knowledge or outside knowledge, in the name of 6i check system, is integrated in the system. Another important aspect is that the system isn't relying on accuracy, but is relying on recall that gives us an accurate measure for solving the actual problem and not for being precise. Alongside consistency and flexibility, the solution has a really short time of both training and both testing. The training time may be not relevant at first sight, but as more and more transactions are flowing each day through the system, we can learn on greater data sets by day. The biggest drawback the system has is the number of false alarms. As I said earlier, a really good recall comes with the cost of maybe lower precision. So when we will have a great safety measure, we will have maybe a large number of false alarms. Future enhancements can be done by implementing unsupervised pre-training. This is because a lot of banking data and a lot of payment systems have unlabeled data. Okay, that's it. And thank you for your attention. I'm listening to any questions.
Thank you very much for your presentation. If I remember correctly, you mentioned that each transaction has 14 features. It's
15,
correct?
15. 15 initial features, and we are extracting more data out of the initial training sets.
So that was the start of my question. So these 15 features are a fixed number, so always all transactions have these features, or you can base your approach on a different subset of this approach or a larger set of such features.
My architecture, it's really a general one given the data I had access to. Different payment systems, let's say Swift or different communication channels, have different payment formats. All the system must be adapted to cooperate with the input given by the communication system.
Okay.
So we must adapt. Yes, I'm sorry to interrupt you. We must adapt to the customer needs. That's what I presented here. It's a general idea of how we can use it, but having different data may cause a different approach or maybe some changes in the architecture.
Okay, thank you. And another question. You mentioned that you experiment with heavily imbalanced data set. It's true, no?
Yes, it is true. But, and for a long period of time, I used only the heavily imbalanced data sets.
But if you try to go to a new transaction mechanism, to another mechanism, maybe you will start with not with imbalanced data set, but with very imbalanced data set. Maybe the whole data set will have no fraudulent transaction, because you mentioned that fraudulent transactions are quite rare, not so often.
Yes, we can have this possibility, but also it is really hard to guarantee to a certain customer that our system will have success with a really poor input data set. So it really depends on the information the customer is willing to furnish it or to put up to.
So you have to tell your customers to prepare data set in order to be able to learn.
Not really prepare data set, but to give us access to a really, really large data set in order to guarantee the success of the current architecture.
And also to have fraudulent transaction in their data set, yes?
Actually, I didn't study that problem, but that can be a further development idea. Maybe the system will work correctly without a fraudulent transaction in the training set, because it really focuses more on corner cases after it's trained. So in general, the fraudulent transactions are, let's say, the black sheep. The system really... Yeah, the black swan, sorry. So the system really learns to aim and to tackle the exception cases, the corner cases, the ones that are not in a certain, let's say, metrics. The cases that seem unusual, not really by blocking the transaction, but by requesting another confirmation that the true owner of the data or of the credit card has made that transaction.
Thank you. Other questions, if there are, please.
Fitting the model when testing it. So the actual testing, training and testing was done using, let's say, batches, because that's the banking system working on. It's working on having some clearing sessions, and that's why I based my system on not of giving instant response, but at a certain time. Let's say we have 10,000 payments already processed and ready to be settled. We are going to settle all of them, and the system is going to label the possible fraudulent one. That's what I've done in testing. As further development, I implemented a complex architecture, or a bigger one, with a consumer and a producer, and a communication channel that resembles how a banking system is really working. And the system is now processing payments one by one. So I really tried to adapt the current architecture to both requirements, either bulk processing or one-by-one processing. Yes, it can, but that's why I really train the system to work also with singular payments. So it's up to the customer. It's up to the way the payment system is actually working. Okay. Okay.
Thank you very much for your presentation. If there are other questions, please, you can all ask questions. Maybe it's interesting, and you can ask questions. Don't be shy if you have. Thank you very much again, and with this, I will try to get through the next presentation. I think Ancuța, Hij, tramways and railways recognition using densely connected networks. Let me see if, yes, Ancuța, Hij, yes, thank you.
Yes, hello everyone. I would like to know if you can see my screen.
In a moment.
Okay.
I will tell you. I see. I don't know if these are tramways or railways, but I see.
Okay, great. Hello everyone, my name is Ancuța Hij, and the topic of my presentation is tramways and railways recognition using densely connected networks. I would like to start by presenting the table of contents that includes introduction and the motivation, challenging in recognition problem from a machine learning perspective, the related work, the proposed approach, the numerical validation, and a short demo if there is enough time, and the final thoughts. According to the National Highway Traffic Safety Administration in the United States in 2008, approximately 2% of the total number of collisions included a car, a tram, or a train. So, The motivation is to build an intelligent system that recognizes the tram lines and rail lines like a human individuals, and this system can be integrated into as an intelligent component within an advanced driver assistance system. From a machine learning perspective, tramways and railways recognition is a binary classification problem where the input consists of traffic frames obtained from video sequences recorded by a camera mounted on a car. The output will be a discrete value which corresponds to label 1. The label 1 indicates the presence of railways or tramways within that image, or label 0, which indicates their absence. It's important to notice the fact that being a classification problem that will not give us any information about the location of tramways within that image. Some challenges that may appear during the learning process, also known as false positive in machine learning, are the following: shadows projecting on the road, white lane marking from the road scene. Two examples can be visualized on the right side of this slide, where one of the classifiers identifies the shadows and the lane marking as being trams lines. What is with red is the output of class activation map, which is a visualization technique for recognition problems. Other challenges are curbstone and sidewalk edges. To these, we add a varied road types, weather, and illumination condition, which make the overall learning process even harder. Well, there is a lack in literature of solution for railways and tramways recognition. Majority of existing solution perform segmentation, not recognition, with images captured from a train, where the lines are always located in front of the vehicle. In our dataset, the tramways railways dataset, the lines may have multiple locations within the road scene. The handcraft feature approaches uses in pixel intensity thresholds, but they are quite limited due to the fact they offer a limited generalization power. Those thresholds has to be known before any computation. The second type uses automated features extraction techniques, where a convolutional neural network was involved. For this neural network, it was trained to identify lane markings on the road scene, not tramways. But we can say that lane markings are transferable to the domain of tramways and railway track. The main disadvantage of this approach is the necessity of a large data set. The proposed approach can be summarized in a few steps, which are the following: data labeling, followed by image preprocessing that includes image filtering, data augmentation. After that, we continued with training. The training focuses on focal loss and class weight. We'll talk about this in the next slides. And from class weights, we derived a classifier which uses active learning. All models, all classifier trained will be tested with different metrics of performance. For a machine learning classification algorithm in traffic environment, we should expect to have tens of thousands of labeled images which accommodate each possible scenario from real life. Our dataset, tramways and railways recognition dataset, have 4,000 labeled samples, where nearly 1,500 with positive sample and 2,500 negative sample, so an imbalanced data set. Data augmentation techniques like like translation, rotation, and cropping were used in order to offer more generalization. Image sharpening was applied also for edge enhancement, and it was realized by using a Laplacian filter using a convolution. An example can be visualized on the bottom of the slide. Training a classifier from scratch on a small data set is a tough task. So in order to perform to obtain great results, I decided to go with transfer learning. The neural network uses a dense net architecture. Dense nets, a successor of residual network, and the main objective is to focus on imbalanced data set and in the same time to keep a small number of false positive samples as small as possible. First techniques that does such a thing is class weight. This technique penalizes harder the positive samples. For this technique, we have two hyperparameters, one for the negative class and one for the positive class. The default values for these parameters are 1. The next technique is focal loss. This technique focuses more on hard to classify example, and it adds a modulative factor to the value of binary cross entropy, which reduces the loss contribution for well classified samples, but penalizes the harder to classify samples. The main difference between class weights and the focal loss is the fact that class weights focuses more on positive samples which are misclassified, while the focal loss takes into consideration both, also the positive and also the negative sample which were misclassified. Labeled data is expensive, but unlabeled data is not. Active learning is a technique that uses human interaction when a certain degree of uncertainty for a prediction is met. The query strategy may be considered the main rule on which the algorithm is based. I use uncertainty sampling with a combination between the least confidence criteria and margin sampling criteria. The least confidence criteria takes into account the largest probability value that has to be larger or smaller than a given threshold. It depends on the type of certainty pool that we are in. It can be high certainty pool or low certainty pool. In margin sampling criteria, the difference of the two largest probability values must be larger or smaller than another given threshold. This also depends on the type of the pool we are in. The images from the high certainty pool are added straight into the data set, but while the images from the low certainty pool are passed to a human individual in order to be labeled. After that, they are also added into the data set. The final of an iteration, active learning is an iterative process. The final of an iteration, the model is retrained, but this time with an enlarged dataset. It is important to mention the fact that active learning starts with an already trained classifier on our dataset, Tramway and recognition dataset, which uses class weights, and the final resulted model is M_ILL. The right side of this slide presents our two plots of model loss and accuracy during the training phase. As you can see in the top plot, the best model which obtained the smallest value for the loss was focal loss, but in the bottom plot there is another model which scored a better uses class activation, uses class weights. On the left side of this slide, you can see the values of metrics which indicates the performance of the classifiers. The red colored numbers represents the best value for a given metric from those four classifiers. Now we have time for a short demo. sequence is loaded, as you can see in the front of the car. There are some railways, but due to sun, they are not very visible. Also, the classifier cannot identify them yet. As you can see, the current label is no, but now the label is tramways and railways. And as the car goes closer to the tramways, the prediction value also increases. And now the classifier is even more sure about the presence within that image of the tramways. I would like to say that the active learning classifier was used for this demo. The railways are still available within our field of view, but if you watch the prediction value, it started to slightly decrease. As you can see, the railways are not that visible. Now they are not sorry, they are not identified at all. Okay, and this is a sequence with no railways at all. Okay. As final thoughts, in order to solve railways and tramways recognition problem, the challenge was to work with an imbalanced data set with a small size. The classifiers were prone to have a large number of false positives, which were previously ignored, but the techniques like class weights and focal loss helped a lot. For a better generalization, I used active learning. As future work, active learning can be extended to query by committee, which is another active learning strategy where multiple classifiers are involved in order to take a decision. Another improvement can be made by changing the goal of the problem to from a recognition problem to have a segmentation problem, which also indicates the location of the railways or tramways within an image, not only a label which indicates the presence or their absence. Thank you. Questions?
Thank you very much. I will start with a very short questions. So in your reasoning, both machine learning and classification, there is no time relation there. So it seems that seems obvious that when you start presenting your demo in the first frames, you didn't see any railways, and the belief in railways was low. But when you start seeing the railways, when you pass through the railways, even if you saw previous railways and there are some railways on the frame, you still believe that the existence of railways it's quite low. So now you didn't see any railways. Now you see, but
yes.
In my opinion, the time should somehow imply that if in a previous frame I saw the railways it's so also in the next
Yes.
in the next frame. So I don't know, near around here, let's say, when you switch from from railways to no railways to green to something
Yes.
like.
Well,
I saw in the previous frame the railways. Maybe I should increase the doubt that also exists.
Okay.
So it's the same value, the same belief, the same probability, but because he occurs after the events, then you have to. So now I will say, because in the previous frame was a railways, maybe it's still there.
Yes, yes, I understand. This may be considered an optimization of the current solution. In the in this presentation, I didn't take into the consideration the value of the previous frames. The model makes a prediction for a given frame without taking into the consideration the value of the previous one. So
So
yeah,
maybe you can
yes,
say that's the probability based on the current frame. But let's say if in the previous frame was a railway, then I have to increase my belief with,
certainty.
I don't know, with
Yes,
10% or something like that, saying that maybe
yes, yes. It is an improvement of the current solution, of course.
maybe there are more complex way to take into account the time, but this seems quite obvious and quite easy to do.
Okay.
Thank you. Other questions, please.
Yes. Uh, Frames with only one frame in the the thing. Well, uh, I no, the majority of exam of the sample from my dataset include two railways within a frame, and I didn't focus that much on the hard to classify samples like when only railway is available, because this thing can lead to unexpected false positives. I also had a problem with reducing the number of false positives. I try with class weights and focal loss. A lot of lines like shadows or curbstone. This is only one line was misclassified as a tramways or railway, and the focus was to have in the most in the most positive sample to have two lines, not only one. Yes. 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 Mhm. Yes. Yes. Other questions?
Yes, in a way, my next question, it's in a way related, was the idea come by listening to the previous questions. So first of all, here you have two parallel lines, but you quite good. It's a quite good presumption that there is no railways, even if maybe seems like railways because there are two separate parallel lines. But the questions in a way related with the previous, it's if you see instead of showing two parallel railways or two parallel lines, you see three parallel lines. Maybe there are railways, but you see just half of a separate railways. Do you will be able to detect that it's also a railways, even if instead of having two separate parallel lines, actually there are three?
Yes. There were many samples where on the road scene were a lot of railways forks, and in the training dataset, so the model was able to identify those examples of course.
Okay, thank you.
Thank you too for listening and for your questions.
Other questions if there are. Otherwise, we have to thank our presenters and to ask to be prepared our next presenters. Radu, I have to apologize. I see very small characters. Radu Galan or Galan, automotive
Galan.
intelligence systems, tunnel recognition using deep learning techniques. It's the same. Ancuța Hâj, I was named Ancuța Hish because I was not able to see special characters in my computer.
It's okay, no worries.
Please.
Can you hear me all right?
Yes, I see some blue screen. It's okay.
Great. I'm going to start then. My name is Radu Galan, and I'm going to present my work on tunnel recognition using deep learning techniques. First of all, in this presentation, we want to present our problem and compare it with the other works that have been done in the field, describe the architecture and briefly the implementation, then get to the interesting part about the model selection and the applied techniques, analyze the results and draw conclusions, and at the end we are going to show a little demo. In the introduction, we are gonna first have to define the problem. Simplified, we have a camera on a vehicle and we want to identify tunnels on the roads ahead of us. And how do we put this question would be the most important part, perhaps. It's a binary classification in its simplest form, a tunnel or no tunnel. It can also be extended to a tunnel with multiple components, the entrance inside of the tunnel and the exit of the tunnel. So how can we use the answer to this question? Actually, there are multiple subsystems running on a vehicle, and we can use this information directly. For example, there's this effect called camera blindness every time a vehicle enters a tunnel because of the sudden brightness change. Also, in tunnels, there is a certain level of pollution, and we want to keep internal ventilation on. Headlights are very important, obviously to be turned on, but also to not point directly at the other drivers coming from the opposite sense. The internal temperature is essential to not create dew or vapor that could create an impediment on the windscreen. Also, we don't want to waste energy on the windscreen wipers. And if we are talking about autonomous driving, then this information could help the system decide what speed to take, what speed to have, if it's the case to overtake and so on. If it's a driver, then we could use alerts about the height or weight of the vehicle before the tunnel. We are going to proceed by presenting the state of the art in the field. We researched on AI methods, but it was a surprise that actually none of them used AI, and all of them used only mathematics and image processing. We've identified 5 works with 2 actually relevant, 2 of them were relevant. The first is created at the University of Parma, and it takes advantage of the fact that when you are in a vehicle, in a sequence, you have 4 states: before the tunnel, right at the entrance, inside, and the exit. They are going to recognize only 2 of the states and suppose the existence of the others by using a histogram, horizontal and vertical, of darkness for the entrance to create a bounding box, and using brightness for the exit with a fixed threshold. The second work comes from the University of Oslo, and it presents multiple methods that are in the end combined. The first one is a simple edge detection with compared with a circular formula, supposing most tunnels are semicircular. Identifies tunnel lights using brightness differences, supposing again that there are lights in a tunnel. Using a little regression to learn formula of an ellipse with half dark and half normal brightness. And a very rudimentary image difference between a template and the image. There are some other works that I have found, but this one is actually a patent that doesn't show any data or results. This is based on radar signal and only applies for iron tunnels. And this is uses GPS data to learn where are the roads and how to find tunnels using the gaps between roads. As you can see, none of them use AI or camera, sensor, image, computer vision. We are going to dive into our application, first by presenting the system. We used as local machine, on the local machine, the IDE and the display. We've used a server to store the data and use the computing power. We needed a shared location to transfer files and share the code between them. On the local machine, we used PyCharm, and on the server, Anaconda environment with all the needed libraries. They communicated. We accessed them actually using MobiXter. The actual implementation, we are going to start with the data that is perhaps the most important. We try to have as large variety as possible with all the seasons, winter, summer, all the daytime periods, either night or day, and multiple sites like nature in the city, and even multiple countries. We've created 3 data sets. All of them are rationed by 60, 30, and 10% for the training, validation, and testing data. And all of them are used in the binary classification, labeled with 0 and 1, and only the first 2 are labeled with 4 labels, manually labeled, so about 18,000 images. Image processing is an important part, but as we experimented with multiple effects and filters, we found out that actually the most rudimentary ones work best on our situation. We only used cropping, resizing, and normalizing. The first project is data augmentation, actually how we create the first data sets. We get the path of the images that we want to label. We transfer them locally. We convert the paths and start manually labeling them on 5 different labels: tunnel, bridge, nothing, both, or irrelevant image. We extract the results and then we create complete data sets well randomized. The second project takes advantage of this data set constructed using models from transfer learning libraries and the given data sets with a whole bunch of parameters that we've experimented with and tweaked. We use convolutional neural networks to train and finally predict images received through the SSH connection we are going to construct in the interface. On the local machine, we have a interface where we can access the server directly and give it commands to predict or even train some of the models. We can see all the metrics and information even about data exploration. The first part was to choose a model. We had more options. We tried to choose different architectures, and we gave them a single data set and let them learn. All of them slightly overfitted, but this is a limited small data set, the first phase, and VGG 16 architecture dominated them all, so we decided to go further with it. I'm going to shortly present it. It's relatively simple with a couple of convolution layers followed by pooling layers. Obviously, it's transfer learning, but it's quite optimized with only 14 million parameters, out of which we trained on 2 million. We wanted to take advantage of the fact that it's already trained and kept the first layers that recognize basic components from an image, and deleted some of the last layers, added new ones for our problem, and retrained it specifically for our situation. Now, the interesting part where the techniques actually, we presented techniques that we applied. There were multiple types of classification we could have done. The most rudimentary, the most intuitive ones are the tunnel classification with binary or multiple labels, but there are also other type of classification that could have been done using the fact that the most popular false positive are found in bridges, and combining bridges with tunnels would probably make a good solution. But due to our dataset, limited dataset, we did not implemented this. We wanted to use those models in a more complex strategy in active learning and ensemble learning. The first method is supervised binary tunneling classification using the second dataset with two labels. It overfitted, quite frankly, on the training, but on the testing phase, particularly chose to be difficult, it achieved 95% of accuracy, which is quite big. We wanted to improve this because we observed some false positives that appeared and added more images with bridges labeled as not a tunnel to be harder to confuse. And although statistically it did not improve, we observed quite an improvement in the number of false positive of bridges. The multi-classification method also used the second phase dataset, also obviously with different labels for each phase. And as you can see here, statistically it did not improve again, but the actual real false positives were really decreased, as all the false positive came from a labeling issue, which is actually an evaluation limitation, which I'm going to present later on. In this situation, from the passing from one state to another, inside the tunnel, out the tunnel, and before the tunnel, when the entrance is slightly visible but was not labeled by the human. We tested them with the same data again, and the results are all of them pretty good and relatively fast, about 10 frames per second. We implemented the active learning strategy. Simplified, we trained the model, predict on a new data set, the good images, the well-predicted images are kept and the others are labeled manually. And then we augment the database and retrain our model. Using this technique, we created 2 versions. All of them learn really fast, and the training phase was insanely decreased, 24 times faster than the original method, and we only had to label about half of the image instead of all of them. It also achieved over 90% accuracy, which is almost the same as the original model. A second version used more iteration and more images, but somehow it didn't need to label so many images. Only 1,000 out of 6,000 images were needed to be labeled by the user. I'm going to present some other metrics. Interesting one. We observed that during the day, as expected, the algorithm worked fine. Surprisingly, during dusk, dawn periods, when there is very high direct sunlight, it also works well. But on the night, it slightly performs worse. We also analyzed manually using visualization methods where are the false positives, and we found that most of them were on bridges and really dark images, but more than that were caused by oscillations in the model precision right between states. To prove this, I'm going to present this example. As you can see in the far left, there is a slight oscillation right before a tunnel is completely visible. That counts as a false negative because I have labeled it manually to be positive. The red line signifies multi-classification and the blue one binary. As you can see, it detects every tunnel, even the short ones, with exit right visible from the beginning. I'm going to skip this. Comparison to the state of the art, we achieved far greater accuracy and surprisingly faster, even though this is only image processing. To this method, at least, we also used very big data sets compared to this method. And compared to the second method, we had 100% transition detection, as they called it, meaning effectively state changes from no tunnel to an entrance to be detected at some point. We detected all of them, as it could have been seen in the previous example, but at a certain point, sooner or later, causing a slight fluctuation and false positives. It was indeed slightly slower, but we managed to use more images. We also experimented with a Raspberry Pi. We wanted to test it out in the real world, but due to the current situation, I did not really manage to take it out there. The limitations are also really important. We only have 10 frames per second, and considering that you would want to run this on a vehicle with multiple other subsystems, it would be quite an impediment. And also, as I mentioned previously, the labeling process was quite confusing because both of these images contain a tunnel, but when do you start labeling it as a tunnel? Because when it's very tiny, it might confuse the model and cause it to not learn precisely what a tunnel is. Here I am going to present a short demo. It's recorded because I do not have access on the laptop that I worked on. Here we can select a model. We have a large variety. I've kept all the trained models. It presents us with some details about it. We can also load a database and explore it. We see the number of sequences, individual sequences, meaning approximate number of tunnels. Tunnel classes distribution, how are the sequences, images actually, distributed by hour, month of the year, country, and datetime, which is a manually added label. We can also load an already existing file with results if you don't want to predict it. Begin an animation, which shows us exactly how it performed. We use this quite a lot to see when does it begin to see a tunnel and how can we improve it. We can also load a bigger data set and visualize metrics and statistics about it, confusion metrics and precision and all sorts. We can also make sure that we upload it and confirm the model, and we can begin a prediction that's going to send a signal to the server, and he's going to start predicting the actual images, and at the end is going to send us a result, but there are quite a lot of images and did not wait through. That was my presentation. Thank you for your attention. If there are any questions.
Thank you very much for actually suggesting in this movie the first question I prepared, that your approach should be named Roadrunner, because that's the running joke about the characters who actually enter the tunnel.
Yeah.
In a way, my question is the same as it seems that these last two presentations are somehow related. You try to recognize railways or tunnels, but and the observation is similar. Just by adding time, I think that you can hugely improve the performance of your classification.
Yeah, I've considered this using an oscillation algorithm that would simply average out the trust the model has in each image, and it would level out eventually.
Yes. Thank you. Other questions, please.
No research from what I found have been made using artificial intelligence. So perhaps there exist, but they are not made public because it's an active field and probably a company interest. But only image processing methods have been published for this particular recognition, tunnel or bridges.
Thank you very much for your presentation. If there are other questions, otherwise I propose to get through the, I think, last presentation, which we are so 10 minutes behind our schedule. Okay, Todera and Liana, it's no problem, we have enough time. Todera and Liana, argumentative agents in explainable AI.
Hello, my name is Liana Toderian and I'm a fourth-year computer science student at Technical University of Cluj-Napoca. Are you able to see my presentation?
Yes.
Okay. My subject for today is argumentative agents in explainable AI. First, a short introduction. I developed a multi-agent system for arguing classification of retinal conditions. Patients are classified in three classes: age-related macular degeneration, diabetic retinopathy, and normal, using volume and thickness values. The retina is split in 9 zones, as you can see in figure A. The volume and average thickness for each zone are computed from OCT scan images. In figure B, we have a transversal section of the retina. Agents learn rules from trained machine learning models and the diagnosis is made through an argumentative process using the interaction between them. Assurances of the system performance and explanation are made using arguments. Assurances and explanations are needed in case of systems which are used for diagnosis. Users can be doctors or patients, and the system must gain their confidence. Also, they have to understand the process by which the diagnosis was made. Despite the great performance of machine learning algorithms, most of them are black box type. Getting transparency for such algorithms can be difficult, but it's necessary if you want a system that explains its results. A similar system is multi-agent-based military health system for the future battlefield. Belief, desire, intention agent model is used in order to distribute the diagnosis process and obtain a more effective and high-performance systems. Agents have the responsibility to control an autonomous sensor network and deal with cases of missing data. Another related work is JSON induction of logical decision tree. That is a library which can be used to create decision trees from agent plans written in agent speak language. We are interested in the reverse process, meaning that the plans must be generated from trained models. Here we have the architecture of the system that consists in two main components. Patient data is used to train the models from which the rules are extracted. The rules are passed to the multi-agent component that consists in agents and their environment. Next, we have a more detailed schema of the machine learning subsystem. Patient data is stored in XML files, and the Python data parser is used to create the dataset. These files contain the computed volume and average thickness value from OCT scans. We have 50 patients with data from multiple visits, and after augmentation, the dataset has over 500 samples. Dataset is pre-processed and used to train three models: a decision tree model, a support vector machines one, and a neural network. After the rules are extracted from models, they are translated in agent speak language, and an SAL file is created for each arguing agent. We will have an agent for each machine learning models, so there will be three arguing agents. The next component is a multi-agent subsystem. It has three arguing agents, a master agent and a human agent. Each agent has goals, action, and knowledge about the domain. Also, they run in a defined environment which has some properties. The three arguing agents have their plans completely generated from machine learning models. They ask for the parameters they need for the diagnosis, and they make the diagnosis and provide arguments for it. Master agent has multiple responsibilities. It interacts with human agent in order to obtain the parameters values, manages the diagnosis process, and handles the conflict resolution if it's necessary. It also gives the diagnosis results and formulates an explanation for it using arguments. The human agent simulates behavior of a real user. It has information about patients and only interacts with the master agent. We use two argumentative patterns. First, a pattern for explaining decisions in medical domain that is used by arguing agents to motivate their diagnosis. So it must include the input parameters for the diagnosis process. Arguments are formulated using the clauses that are checked during diagnosis process. We have a template for one clause, but the final explanation can be a combination of multiple arguments. Here we have a simplified version of assurance argumentative pattern adapted for a multi-agent system. The original pattern is a more complex one and is used to give performance assurances for a system prior to its use. This one is useful in getting user confidence and resolving agent conflict. The performance evidence is given to the user as assurances. It consists in machine learning performance score and agent's confidence in diagnosis. This pattern helps to create a complete explanation that the user needs in order to trust the process that led to the diagnosis. User will know how sure the agents are of the diagnosis they made and how well they learned. Machine learning subsystem is implemented using Python scikit-learn library. Trained models are classifiers defined in this library, and it also provides function for preprocessing data, splitting data in training and testing set, and computing score performance for test. Here we have an example of rules. They have the structure of a conditional statement, and each return indicates a possible diagnosis if the clauses are respected. The output is the probability that a sample belongs to each class if its volume and thickness values respect the given conditions. Only the parameters that are relevant in the classification process are compared. From decision tree model, the rules are obtained by traversing the tree from root to each leaf. The clauses are collected from each node on the path, and the output is in the leaf. From support vector machines and neural network models, the rules are obtained using rule matrix surrogate. It contains a rule list with clauses and output for each list item. For the argumentative agent, we used JSON. JSON is a tool for implementing agents in an extended version of agent speak language. We chose JSON because it's one of the most robust and used tools for creating multi-agent systems. The plans of the agents are written in agent speak, but the environment and the system behavior can be modeled using Java code. An agent plan is composed of triggering event, context, and body. The plan handles the event in the specified context through a set of actions. Agents also have beliefs, plans, and intentions. They react to changes in the environment or in the belief base. We can see also an example of arguing agent plans generated from the rules. The conflict resolution process has three factors: majority vote, confidence in the result, and performance score. First, the master agent tries to solve the conflict using majority vote. If two agents make the same diagnosis and only the third one has a different vote, then it is most likely that the one chosen by the majority is correct. If this is not possible, it makes a compromise between the agent that is the most confident of its diagnosis and the one that has the highest performance score. Average between confidence value and score is computed, and the agent with the highest average wins the argument. Here we have an example for each conflict resolution cases. In the first one, two agents agree with each other, so the conflict can be solved by majority vote. The master agent gives their confidence and performance score as assurances. In the second one, all three agents have different opinions, and the most confident one that has the highest performance is chosen. In both cases, the human agent is informed about the conflict and how it was solved. This is an example in which the agent master formulated a complete explanation of the diagnosis result using the arguments from agent 1. Now we'll talk about results. The multi-agent system allows interaction with the human agent and makes explained diagnosis for which it provides arguments. The system assurance arguments consist in confidence and performance score, very useful in conflict resolution and for the user. Diagnosis process is very effective because the agents run in parallel. A report with the final diagnosis, arguments, and conflict resolution is sent to the human agent. The classification is made using 3 different models. We obtain over 90% accuracy for the decision tree and neural network models and 75% for support vector machines model. In conclusion, the system achieves high performance of machine learning algorithms and ensures transparency through arguments. It also gives assurances for its performance using model test scores. After the rules are extracted from the trained models and translated in agent speak, the agents and their environment must be created. It can be extended by adding more agents capable of making the diagnosis with plans that are generated from more complex machine learning algorithms. Also, by considering more features in the classification process, the explanations can contain more and stronger arguments. Thank you, and if there are any questions.
Thank you very much for your presentation. If there are any questions, please. So in your experiments, you always try with 3 agents, or it could be more than 3 agents, or always should be an even number of agents or something like that? Or?
No, there can be any number of agents, but currently we are using only 3 machine learning models, but we can use any number.
But having clone agents, so let's say you have one machine learning agent, and if you clone many times the same agent, maybe you will be able to have a more biased learning.
Yes, if it's necessary, we can clone the agents, but only if the diagnosis has to be made simultaneously for more patients.
And if did you try with more complex domain, or how many rules do you have in your agents? 1,000, 100 of rules, tens of rules?
There are, for the decision tree models, there are more rules, but for support vector machines and neural network models are 5, 6, because currently we use 18 parameters for the classification.
Okay, thank you.
Thank you.
Other question?
Yes, but it will be a development of this system.
If that will be all, let me acknowledge all your work. Also have to thank the last presenters, and I have to thank all of you who attend this conference. As an administrative questions, I have to ask. It's maybe you have experience. Should I end the panel, or we will meet again at 1 o'clock in? So at 1, you will make a short break, let's say, at and we will meet again in the general teams at 1 o'clock. Yes, it's okay.
Yes, thank you.
Thank you very much. Goodbye.
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 Salut!